Space may seem empty, but it's actually full of gas and dust. These clouds, called nebulae, are the birthplaces of stars. Imagine a giant cloud of hydrogen and helium drifting through the vastness of space. This is a molecular cloud, a stellar nursery where stars are born. These clouds are cold and dark, but within them, gravity is at work, pulling matter together. Over millions of years, gravity draws in more and more gas and dust. The cloud begins to collapse under its own weight, squeezing the material at its center. As the cloud collapses, it fragments into smaller clumps, each destined to become a star. Think of it like a cosmic dance, with gravity leading the way, orchestrating the birth of countless stars.
As the protostar continues to gather material, its core gets hotter and denser. The temperature and pressure at the center eventually become so intense that nuclear fusion begins. This is the process where hydrogen atoms fuse together to form helium, releasing an incredible amount of energy. Imagine the power of a billion hydrogen bombs exploding every second. That's nuclear fusion. This release of energy creates outward pressure that balances the inward pull of gravity. The protostar stops collapsing and achieves a state of hydrostatic equilibrium, a delicate balance between gravity pulling inwards and pressure pushing outwards. The protostar is now a true star, shining brightly with the light of a billion suns. Stars come in different sizes and temperatures. Our Sun, a yellow dwarf star, is relatively small and average, but there are stars much larger and hotter than our Sun, and others smaller and cooler. The color of a star depends on its temperature, with blue stars being the hottest and red stars the coolest. The life cycle of a star is determined by its mass. Massive stars live fast and die young, while smaller stars like our Sun live for billions of years. It's like comparing a sports car to a family sedan. The sports car may be faster and more powerful, but it burns through fuel quickly, while the sedan is in it for the long haul.
For most of its life, a star exists in a state of delicate balance. Gravity constantly tries to pull the star's material inward, while the outward pressure from nuclear fusion in the core pushes back. This balance is what keeps a star stable and shining for millions or even billions of years. Think of it like a cosmic tug-of-war, with gravity and pressure locked in an epic battle. During this stable phase, a star fuses hydrogen into helium in its core, releasing energy in the process. This energy makes its way to the star's surface, where it radiates out into space as light and heat. This is the light and heat that we feel from our own sun, and it's the reason why stars shine so brightly. As a star ages, it gradually consumes the hydrogen fuel in its core. The more massive a star, the faster it burns through its hydrogen fuel. It's like a car with a bigger engine. It might be more powerful, but it also guzzles gas. Our Sun, for example, has been fusing hydrogen for about 4.6 billion years and has about 5 billion years of fuel left.
While our Sun is a relatively average star, the universe also harbors true behemoths, massive stars that dwarf our Sun in size and power. These stellar giants live fast and die young, their existence a cosmic spectacle of breathtaking proportions. Imagine a star so large that if it were placed in our solar system, it would engulf all the planets out to Jupiter. Massive stars are like cosmic pressure cookers. Their immense gravity creates incredible pressure and heat in their cores, causing them to burn through their hydrogen fuel much faster than smaller stars. While our Sun will live for about 10 billion years, a star 10 times more massive might only live for a few million. As a massive star ages and consumes its hydrogen fuel, it begins to fuse heavier elements in its core. This process releases even more energy, causing the star to expand outwards into a red supergiant. These red supergiants are among the largest and most luminous stars in the universe.
Section 5. The fuel runs out, a star's impending doom. Eventually, even the most massive star will exhaust its nuclear fuel. The outward pressure from fusion weakens and gravity, always lurking in the background, begins to take over. The star's core contracts under its own weight, becoming denser and hotter than ever before. Imagine a building with its supporting beams slowly giving way. That's what's happening inside a star as its fuel runs out. The core, once the source of the star's power, is now on the verge of collapse. As the core collapses, the outer layers of the star are left with nothing to support them. They begin to fall inward, pulled towards the collapsing core by the relentless force of gravity. This infalling material gains incredible speed, like a roller coaster plummeting down a steep drop.
Section 6. Core collapse. The beginning of the end. The core collapse of a massive star is a cataclysmic event. Imagine the entire mass of the Earth squeezed into a sphere just a few miles across. That's the kind of density we're talking about. As the core collapses, it becomes incredibly dense and hot, reaching temperatures of billions of degrees. At these extreme temperatures and densities, the laws of physics as we know them begin to break down. Protons and electrons are forced together, forming neutrons. The core is now a giant ball of neutrons, resisting further collapse due to neutron degeneracy pressure. The infalling outer layers of the star slam into this incredibly dense neutron core, creating a shockwave that propagates outwards. This shockwave is like a cosmic tsunami, carrying with it an unimaginable amount of energy.
Section 7. Supernova. A star's grand finale. The shockwave generated by the core collapse rips through the star's outer layers, blasting them into space with incredible force. This explosion, called a supernova, is one of the most violent events in the universe. Imagine a billion suns exploding at once. That's the power of a supernova. The supernova shines brighter than an entire galaxy for a brief time, outshining all the other stars in its vicinity. It's a cosmic fireworks display of unimaginable scale, visible across vast distances. Supernovae are essential for life as we know it. The intense energy of the explosion creates heavy elements, like gold, silver, and uranium, which are scattered into space. These elements eventually become part of new stars, planets, and even life itself. We are all made of stardust, forged in the fiery hearts of dying stars.
Section 8. Stellar remnants, neutron stars and black holes. After a supernova, all that remains of the once mighty star is its incredibly dense core. Depending on the mass of the original star, this core can become either a neutron star or a black hole. Neutron stars are incredibly dense objects, packing the mass of the Sun into a sphere just a few miles across. They are like giant atomic nuclei held together by gravity. Some neutron stars spin rapidly, emitting beams of radiation that sweep across space like cosmic lighthouses. If the core of the collapsed star is massive enough, even neutron degeneracy pressure cannot withstand the force of gravity. The core continues to collapse indefinitely, forming a black hole.
Section 9. Black holes, gravity's ultimate triumph. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They are like cosmic vacuum cleaners, sucking in anything that gets too close. Imagine a place where the fabric of space-time itself is torn apart, where the laws of physics as we know them no longer apply. That's a black hole, a region of infinite density and zero volume, a singularity in the fabric of the cosmos. Black holes are invisible to telescopes, but their presence can be inferred by their effect on nearby matter. As matter falls into a black hole, it heats up and emits radiation, creating a bright disk of accreting material.
Section 10. Conclusion, from dust to black holes and everything in between. The journey from a collapsing cloud of gas and dust to a black hole is a testament to the power of gravity and the incredible cycles of stellar evolution. Stars are born, they live and they die, and in their death throes they create the building blocks for new generations of stars and planets. The universe is a vast and wondrous place, filled with objects and phenomena that challenge our understanding of physics and push the limits of our imagination. From the birth of stars in cosmic nurseries to the death throes of supernovae, the cosmos is a never-ending spectacle of creation and destruction. A cosmic dance that has been playing out for billions of years.